So if you left a bottle of gasoline in the sun with the top off and came back a few days later, you would have lost gasoline to evaporation. And if you sealed the top on tight of the bottle would bulge out due to the pressure. The same thing happens with a gas tank on a car. Gasoline is going into there that could have been used to power your vehicle and increase your fuel economy. 2 to 4 miles per gallon is possible. That's your dollars floating away. Additionally, the fumes add additional pollution to the environment and a possible safety hazard if they light off. So car designers made the EVAP system to capture the fumes and burn them in your engine. EVAP stands for Evaporative Emission Control System. There are various designs, but on the 1997 Ford Escort and Mercury Tracer, as well as the 1995 to 1997 Ford Ranger, and as well as various other mid-90s Fords, Ford used the Evaporative Emissions Purge Flow System. Let's take a look at that system. The fumes build up pressure in the gas tank here. They pass through the fuel vapor vent valve that separates fumes from the liquid with a float. The fumes travel to a charcoal canister by the pressure generated by evaporating. That's this piece right here. The fumes are absorbed by a highly porous form of activated charcoal. Any excessive pressure is released to the atmosphere after removing the fumes. The fumes are actually stored as a liquid in the pores of the carbon. This is due to capillary condensation and surface tension in the pores of the carbon. But that's beyond the scope of this video. So the computer uses a variety of sensors to make the decision about when to release those stored up fumes here into the engine. And it looks at an engine coolant sensor, an intake air temperature sensor, a throttle position sensor, a mass airflow sensor, and a vehicle speed sensor. It does this so the engine will run properly. If it just opens it up any old time, it could cause the engine to run very poorly and possibly even stall out. The computer will never release the fumes in the charcoal canister to the engine when it's just at an idle. That would probably cause it to stall out or stumble. Instead, the computer will wait until the engine is warm, stable, running at moderate load, and at open or part throttle position. When the computer is ready, the gasoline in the charcoal canister is released by this electromagnetic purge valve, also known as a solenoid. Here's a nice blown up view of the one that's used in this system. When the solenoid receives electricity, the magnet turns on and lifts this little valve here. It'll apply vacuum to the charcoal canister, and fresh outside air will be sucked into the charcoal canister. This will cause the gasoline trapped in the activated carbon to release itself and be sucked into the engine for burning. So the computer actually sends a variable electric signal to the solenoid, similar to if you were rapidly flicking a switch on and off. Except the computer is doing it very rapidly, many times a second. This is known as a duty cycle signal. The more on time the solenoid has, the higher the percentage of duty cycle. The less on time it has, the lower the percentage of duty cycle. This controls the quantity of fumes passing to the engine, as just opening the valve wide open suddenly will cause the engine to run poorly. The final part we have in this system is the purge flow sensor. The purge flow sensor measures the quantity of gas that is flowing. This lets the PCM, or computer, know if there's a leak or a blockage, if the gas is flowing when the valve should be closed, or not flowing when the valve should be open. So it knows whether this solenoid is opened or is closed. This lets the computer or PCM know if there's a leak or a blockage somewhere in the system. It does this because if the solenoid is supposed to be open and it doesn't detect any flow, then it knows there has to be a blockage or perhaps a broken hose. Alternatively, if the solenoid is supposed to be closed and yet it's still detecting flow, it knows that there's probably a leak somewhere, including in itself. This is a picture of Ford's patent for their purge flow sensor. It's composed of a simple circuit shown here. This type of circuit is known as a voltage divider circuit. It takes an input voltage, in our case about 12 volts, and outputs a smaller voltage, ideally 0.4 volts to 4.8 volts. This is known as a signal voltage. It lets the computer know whether gas is flowing on the higher scale or whether gas is not flowing on the lower scale. The way it works is it's composed of a resistor, shown here, and a thermistor, shown here. A thermistor is a special type of resistor. When electricity passes through a thermistor, it heats up. It would hit its highest temperature when no gas was flowing. A thermistor has a special property in that as it gets higher temperature, it gets higher resistance. And as it gets higher resistance, you get less voltage output. So you'd be looking at the lower end of the scale. Realistically though, you're looking at about 1.3 volts with aftermarket parts. However, when gases start flowing through here, it starts cooling off. And the more gases that flow, the more this is going to cool off. So you get a lower temperature, lower resistance, and more voltage output. In the real world, with aftermarket parts, you're probably going to get about 4.95 volts output. Furthermore, the lower side of the figure you should be seeing at idle, because at idle, this solenoid should definitely be closed. Keep in mind that the solenoid is going to be constantly varying how much air is flowing through this purge flow sensor and how much cooling effect as a result it receives. So as you drive, it's going to be constantly varying between these two extremes. You might see 2 volts, you might see 4 volts, you might see 2.5 volts. Additionally, if this system is leaking and it's a very cold winter day, you can see some extreme voltages, such as all the way up to 6.5 volts. Or it's a very hot day out, you might see a somewhat lower voltage than the typical 1.3 volts I read while driving my car during the wintertime.